What's up, guys? It's Matt's Math Tutorials back at it again with another video. More AP practice. Yeah, let's get into it. Let f be the function given by f(x) equals e to the negative x squared. Write the first four non-zero terms in the general term of the Taylor series for f about x equals 0. So, for this one, you could do like a Taylor series thing where you find like, f0, you find f prime, nope, f prime 0, find f double prime 0, all that stuff. But I don't really feel like doing that because it kind of sucks. And we can use something we already know. So this looks pretty similar to just e to the x. And so what we can do with the Taylor series is actually just write out the Taylor series for e to the x and then substitute negative x squared in for every time we see x. And apparently it just works out that way, which is really nice. So e to the x um, is pretty simple. It is just, let's see, 1 over 1, I think, plus, let's see, x over, well, okay, so to make, let's maybe see the pattern a bit better. So 1 over 0 factorial plus 1 over, well, the coefficient in the numerator is always going to be 1, so we can just do this. X to the 1 over 1 factorial. And actually, what I can even do is, oh, wait, yeah, I can even do this. I can say x to the 0 plus x to the 2 over 2 factorial plus x to the 3 over 3 factorial. How many terms do we want? First four non-zero. So those are all going to be non-zero. And then the general term. So plus x to the n over n factorial. So that is it for the e to the x. But now we want to plug in negative x squared. And so, of course, anything to the 0 is just going to be 1. And 0 factorial is 1. So the first term is just going to be 1 plus x to the first power. By the way, this Taylor series for e to the x, that's kind of one you just have to memorize, unless you want to just derive it every time, which you probably don't. Um, Not that deriving it that time every time is necessarily hard, but it's pretty easy to memorize. Just x to the power over whatever the power is factorial, right? Because these always correspond, which makes it much easier. Then some of the other ones like sine and cosine are a little bit harder to memorize, but this one I think you could reasonably memorize. So now replace x with e to the negative x squared, or no, with just negative x squared. So that would be negative x squared, yeah, over 1 plus negative x squared over 2 factorial plus negative x squared to the third over 3 factorial, etc. And I'm going to hold off on writing the general term. I want to simplify this a bit more. So that's going to be 1 minus x squared plus the squaring is going to get rid of the negative, but it's going to make that x to the fourth. So x to the fourth over 2 factorial. And then the cubing is not going to get rid of the negative, but it's going to make it x to the sixth. 3 factorial. And so what we're getting is seemingly negative 1, because it's going to alternate. So we want negative 1 to the n, which will make it alternate, times x to the 2n. All right, and so that kind of takes into account the 2 that you get from the x, negative x squared, and also the negative that you get from the negative x squared. And that kind of just like subs in with the n here, right? This one. Kind of just distributing that n to both of them, right? Those are supposed to be arrows. Anyways, and then divided by, of course, this is just going to be n factorial, right? N factorial. So this is the general one. So, and yep, this is the correct answer. Of course, if you're actually writing it, you might want to make this just 2 and make that just 6. But I don't see why they wouldn't accept this. So that's part A. So that just hinged on the fact that we know e to the x, right? And then we can just substitute in every time we have x, we just write negative x squared. And that'll work even if you have something like sine, sine x squared. You can just do this Taylor series for sine x and then substitute in x squared for, well, I guess that'd be the other way, x squared for x later, after you already do the Taylor series, if you happen to remember it. Um, Although technically this is a Maclaurin series, so I guess it only works for that kind of. But a Taylor series about x equals 0 is just a Maclaurin series. Use your answer for part A to find the limit of this. So, of course, I'm looking at this limit, and it's seeming like, okay, can you just plug in 0 for x? No, because that right there is going to be 0. And we're going to divide it by 0, and that is not good. Also, the top's going to be 0, it seems like, right? Because f of 0 is 1. Yeah, f of 0 is 1. So, actually, yeah, well, plug in 0, e to the 0, 1. So that's top 0 going to be 0, the bottom is going to be 0, which means we can lose L'Hopital's rule. So what we can do is take the derivative of both the top and the bottom. So this is going to turn into, all right, we use L'Hopital's, it's spelled something like that. Derivative of the top, that's going to be 0, that's going to be negative 2x minus f prime of x over 4x to the third. So now what? We have 0 on the bottom still, 0 minus f prime, 0 is still 0. Or is, yeah, so, well, yeah, that's going to be 0. So we can use L'Hopital's rule again. And basically what's going to happen is they're just going to use it until this bottom here doesn't have an x in it. Because, of course, if it has an x in it, it's still just going to end up being 0. You kind of don't want that. So use that again. That would be negative 2 minus f double prime of x. Yeah. Divided by, what would this be? 3 times 4, 12x squared. And then let's do it one more time. That would be just what? Negative f is negative, right? Yeah. Negative 1, 2, 3. Third derivative of f of x, 24x. And let's do it one more time. So f 1, 2, 3, 4 of x over 24. So what is the fourth derivative of f at 0? Because of course now we're going to go limit as x goes to 0. Well, that would be, let's see, fourth derivative, that means we're going to have this one right here. This is the term that's going to matter, I believe. So if we differentiate, right, because if we differentiate, this is going to go to 0. After 4 differentiation, this one's definitely going to be 0. This one's not going to be at 0, but it's going to have x in it, and we're putting in x equals 0. So this one and anything after it is just going to end up being 0. So this is the only term we care about. So if we differentiate that 4 times, we're going to get, what, 4x to the third over 2 equals, what, 2x to the third, and then we're going to get 6x, we're going to get 6. No, we're going to get 6x squared, and then we're going to get 12x, and we're going to get 12. So the fourth derivative of that is 12. So that would be 12 over 24 equals 1/2. So the limit of this at x goes to 0 is 1/2. Now the problem is I think I did something wrong. Because for this to work, for L'Hopital's rule to work, you have to make sure that it's 0 over 0 for all of them, which I'm not entirely sure of. So let me double check that. we just double check this one, right? First derivative is 0. Oh, it looks like every odd derivative is going to be 0, right? Because um, if it's like the third derivative, right, that's going to be 0, I think. And then these are all just still going to have an x in it, I believe. So yeah, so if you do derivative once, it'd be 2x, twice would be 2, third would be, right. So that means that, what, this one's 0, this one's 0, which makes sense because we want that to be 0 minus 0. That one's 0, and then what is the second derivative? That would be, what, 2? Negative 2 minus negative 2. Oh, it is 0. So actually we're good. Because the this answer key I'm looking at is doing it in a different way where they use the actually I don't know what they're doing. Yeah, honestly, could not even tell you what they're doing at this answer key. I think they're writing it as like a sum first, but honestly, this way makes a lot more sense to me. So I'm just comfortable calling it 1/2 based off that, using L'Hopital's rule like 4 times. Seems to make sense. Write the first 4 non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0. Use the first 2 terms of your answer to estimate this. Okay, so this is easy enough. Once we get the answer for the first part, we just plug in 1/2. So that's easy. So the real thing is getting this. Now you can pretty much ignore the like t and x because this is like kind of just like chain rule. It's gonna like this is t is gonna be a dummy variable, so we can kind of just keep the x. So write the first 4 non-zero terms of the Taylor series for this. So basically, if we take the first 4 non-zero terms of the Taylor series for our original thing, we can just integrate each one separately, and it'll give us the first 4 non-zero terms of the Taylor series for the integral of our thing. So let's do that. Um, let's rewrite it. So it's 1 minus x squared plus x to the 4th over 2 to, sure, minus x to the 6th over 6, right, 3 factorial 6. Now we just integrate each one of these terms. Integral of 1, and it looks like it's just going to be like the basic reverse power rule for all of these. So 1, that'd just be x minus x to the 3rd over 3 plus x to the 5th over 5 times 1/2, so that'd be 10, right? Because you want this multiplied by 5 to be 1/2, to be, x over 2 still. And then minus x to the 7 over 7 times 6, 42. So this seems to be pretty much our answer, and it looks like that matches up with the answer key. So pretty simple. That's the main advantage, because integrating like this thing uh, is like kind of sucks, not gonna lie. But integrating just a bunch of different terms added up together, that means you can do them separately, and that ends up being a lot easier because a lot of cases like this one, you can kind of just use the power rule kind of in reverse to integrate. So we did that, and then use the first 2 terms of your answer to estimate your to 1/2. So of course we want, we would do something like this, 1/2 to 0, or 0 to 1/2, I mean. But clearly, if you plug in 0, you're just going to get 0. So you're going to get, the antiderivative at 1/2 minus 0. So you're just going to find the antiderivative at 1/2. So we're just going to plug in 1/2 and not worry about the, from 0 to 1/2 part, if that makes sense. So we have 1/2 minus 1/2 to the 3rd is 1 over 8 divided by 3, 1 over 24, plus 1/2 to the 5th, which is what, 1 over 32, so it'd be 1 over 320. Oh, I'm stupid. It said use the first 2 in the series. Yeah, that's why you read the directions carefully, because I almost did more work than I had to. Use the first 2 terms for your answer. So, okay, this is pretty simple. Change this to 12 over 24 minus 1 over 24, clearly 11 over 24. Okay, so because those are our first 2 terms. Easy. I've never been consistent with the way I do the slash marks. So if that bothers you, I'm sorry. Actually, if that bothers you, I'll change it right now. Explain why the estimate found far exceed difference from the actual value by less than 1 over 200. So I actually almost kind of like gave away the answer for this, but basically we're looking at an alternating sequence where the value gets smaller each time. which you can see because um, we're plugging 1/2, which means 1/2 to the bigger power is going to be smaller each time, and also the thing is divided by is also going to be bigger each time. So these are getting smaller, which means we're kind of looking at something like this, right? Starting here, going down, that kind of represents like this thing right here, and we're going up, but we're not going back up as far. That's kind of like adding this, and then we're going down, but not down quite as far. That's this, and then if you do like an infinite series, because of course they're going to be equal if you look at like the infinite series of this, like this, but going on forever. And if you did that, it would kind of just do this type of motion forever. And of course, the actual answer would be this, whatever it trends to. But basically, the idea here is that because it's getting smaller each time and it's alternating, we did like the first two terms, so this and this. So we're going to add this third term. So it has to be, right, this is that third term we're going to add. So your answer has to be somewhere in this region, right? Because it can't be further away than that because it's going to go up, but then it's going to go back down and up less and then down less and up less and down less. So we already know it's somewhere in this region. So it's within whatever the third term is of the second term. So the third term, if you plug in 1/2, that'd be 1 over 32 times 10, 1 over 320, which is less than 1 over 200. So this distance right here basically is 1 over 320. And we know it has to be within that. And of course, 1 over 200, this is smaller, which means the whole thing is bigger. So that would be up like here, right? This whole thing would be 1 over 200. And so we know we definitely um, are within that 1 over 200 because we're within the 1 over 320 of the answer. So our error is less than that. Of course, this also extends the other direction as well, technically, but like pretty clearly it's going to be like higher than it. So just for the sake of this illustration, I did that. But yeah, we're definitely going to be within this because the next term is less than that. And it's always going to change by the less than the next term. So, oh, I didn't actually type it out, but that was my explanation. Hopefully that makes enough sense. I think that's one of the simpler concepts, the whole like error thing with an alternating sequence. Um, but I do like this diagram right here with the diagonal lines. I think that kind of helps. Um, although it does make it kind of complicated that's moving this way. Ideally, you'd really just be here, here, and then down, and then up again, and then down, and then up, and then down, and then up. But it obviously is hard to see if you make it all in one vertical line. But yeah, so this problem is not too hard. It's just a little like Taylor series. I think honestly the hardest part about this is realizing that if you have this, you can just plug in the negative x squared like this. I think once you do that, honestly the rest of it's pretty easy. Um, but of course, as usual, if you have any questions, leave it in the comments, or if you think that I could have done better in some way, which I probably could have, leave your suggestion in the comments. But for now, good luck on your tests and stuff. See you next week.